Thank you. Thank you for inviting me to give this tutorial on hardness of approximation in parameterized complexity. I've boldened the word recent because I'm going to be talking of things that appeared more or less this week, which is some exciting progress on some very important problems. So this is going to be as recent as one can be. So the outline of the talk is as follows. I want to first cover three important problems in parameterized complexity and their inapproximability results. One is the set cover problem, the other is set intersection, and the final one is clique. And after that, I want to go into the hardness of approximation of k-clique, which we have seen a lot of progress in the last year, and compare it with the NP world and how things are right now. And finally, in the last part, I want to make some high-level remarks which sort of tell the future direction and so on and so forth. So the first part, let us try to motivate why we are interested in studying this area to start with. We are interested in optimization problems, and it turns out that many of them are NP hard. And a natural way to cope with NP hardness is to look for approximation solutions. So suppose exact is computing is NP hard, then what about approximate solutions? And sometimes it turns out that that is NP hard too. Okay. Like for instance, vertex cover, it's NP hard to even approximate it to say 1.1 factor. Then our other coping mechanism is to look for cases when the optimal size, the size of the solution is small. And there we look at fixed parameter tractability. And in the case of vertex cover, it is fixed parameter tractable, so we are in good shape. But then there are some problems like set cover or clique or set intersection, each of which I will define in a few minutes, in which it's hard to cope on both fronts. That is, we don't have very good approximation algorithms, and they are not fixed parameter tractable. And in this case, one idea to look forward to is to combine the two things and ask for, is approximating any of these problems fixed parameter tractable? Or more precisely, we want to ask for, are there FPT time algorithms? So f of k times poly n for some computable function f, where k is the parameter of the problem, that approximates the solution to a factor t of k for some computable function t. So more precisely, let's look at a few examples. So in the case of set cover problem, we are interested in computing if given a collection of n sets. For the sake of simplicity, I've assumed the size of the universe and the number of sets are the same thing. Given a collection of n sets over a universe of size n, are there k sets in our collection whose union covers the entire universe? Now, there's a simple greedy algorithm that gives a ln n approximation, and you cannot do better. So even getting 0.99 times ln n is NP hard. So we are stuck at this ln n barrier. So what about parameterized complexity? It is W2 complete. It's one of the classic canonical W2 complete problems. And it turns out that you cannot even approximate it in FPT time, because we know that in the one hand that it's W1 hard for any to approximate it to a factor f of k for any f. That means that if there is a set cover of size k, even to find a set cover of size f of k for any computable function f, say 2 to the k, is still W1 hard. And this can be even further strengthened to saying, okay, if there is a set cover of size k, to find a set cover of size log n to the 1 over epsilon k for any function, unbounded function epsilon times k is still W1 hard. So we have a reasonable understanding of the set cover problem. And there are obvious open questions as to whether you can still bridge the gap between the greedy algorithm that we have and the W1 hardness result. And this can be both an algorithmic question and a hardness of approximation question, in the sense that instead of poly time, if we are given FPT time, can we beat the Lannan approximation algorithm? Can we beat the Lannan approximation guarantee? And from an hardness point of view, can we go up from log n to the 1 over epsilon to say square root log n, something that's independent of k in the exponent? So let's look at another problem. And this is a very interesting problem that I've chosen because of its status in the NP world. So we're looking at the set intersection problem, where given n sets over a universe of size n, you want to pick k sets whose intersection is maximized. So when I say the intersection, it's all those elements in the universe that are there in each of the k sets. And it's a fascinating problem because in the NP world, even ruling out a p-tas, assuming just NP not equal to p, is still open. So we don't have a good understanding, unlike the set cover problem. Even in the NP world, we don't have a good understanding of this problem. So the best hardness of approximation result we have in the NP world is that there are no polyfactor polynomial time algorithms, but not assuming p not equal to NP, but a weak form of ETH, exponential time hypothesis, that say 3 sat requires 2 to the n to the epsilon time. And this relies on extremely heavy machinery, like the quasi-random PCP of code. Now, so one would expect that if in the NP world we don't understand this problem at all, it should be our understanding in parameterized complexity should be even worse, because that is traditionally the intuition. But surprisingly, Bin-Kai Lin showed that this problem is W1 hard to approximate to n to the little o of 1 over square root k factor. And this is a very surprising result for many reasons. One, that it is a surprisingly relatively easier proof. And it is one of the first hardness of approximation results that we had. And we got sort of this really huge result when we had nothing to stand on. So this came out of nowhere, really. And it's really a very breaking result, like a breakthrough result. And so it sort of breaks this intuition that even if you don't understand the complexity in the NP world, it might be that we, given the power of parameterized complexity, that we can run exponential in the witness size or the solution size, sort of we can benefit something out of it and develop techniques which didn't work in the NP world. And if anyone is interested in looking at the proofs of either the k-set cover or k-set intersection, I have given tutorials on this in the past, and their videos are available on my webpage. But what I want to focus on is the k-clique problem. Because the k-clique problem sort of, despite a lot of effort, we had made no progress on it from a hardness of approximation point of view, proving W1 hardness of approximation point of view. And suddenly in this year, we are able to make some very exciting progress. And I want to talk about that a lot more.
Sorry, can I ask a question about the previous slide?
Sure.
This hardness result. So if you get a larger k, then you get a lower bound.
Yes, in fact, if k is n, then this lower bound is almost meaningless.
Yeah, so that's because you are given more time in the FPT setting, or so.
Right, you inherently
becomes harder for a higher parameter. But
right, exactly. So it's using, somehow it manages to find a technique that exactly utilizes that fact.
And we have nothing even close to this low bound, I suppose. But,
in the NP world?
Well, this is in the FPT world. So there, it's not even close of an FPT algorithm that approximates better and better.
Oh, no, I think the answer should be really very high. I mean, because we have evidence that the answer should be, there should be no good FPT algorithm based on gap ETH.
Okay, thanks.
Yeah, that's a good question. So let me go back to the k-clique problem. So here you're given a graph G, and you want to determine if there are k vertices in this graph which form a clique. And again, let's look at the trivial algorithm. You output any vertex in the graph, it's a trivial k approximation because you have at least one out of the k things. So k approximation is trivial. And the question is, can we do better? And in the NP world, where k can be linear in n, we show that even to get n to the 1 minus epsilon factor approximation is NP hard. And sure, even in the NP world, you can say that n approximation is trivial, and you can do slightly better than n, like say n over polylog n, but really nothing better than that. And we have very tight understanding. So this is a very, very hard problem. And in the NP world, we have more or less understood it. So what about the FPT world? So exactly to solve it, it's the canonical k-clique problem, which is W1 complete. And we believe it's very hard. And very recently, in this last talk 21, we made the first non-trivial progress when it comes to W1 hardness. And we're able to show, Bing-Kai Lin showed that to approximate it to any constant factor is still W1 hard. So given a graph on n vertices, if there is a clique of size k, to find a clique of size k over 100 is still W1 hard. Okay, so this is a great, I would say, a very big breakthrough result. More than the result, it sort of highlighted so many nuances, which I'm going to talk about in the coming slides, which have implications to the NP world, that he manages to find these very subtle observations that are very useful. And more recently, just building on his framework in a joint work with Subhash Kot, we are able to show that we can extend this result to show that given a graph, if there is a clique of size k, then finding a clique of size k over polylog k, or k over how many ever you want, k to the 1 minus little o of 1 size k, clique is still W1 hard. So it's almost polynomial factor W1 hardness. And I want to talk about mainly Bing-Kai Lin's proof ideas, and then a few words about how we extend it in our recent work. Okay. But before I talk about any of these things, I want to highlight some high-level comments that really the big prize that's there in this area of hardness of approximation and parameterized complexity is what is called the parameterized inapproximability hypothesis. So I want to define this. So to do that, I need to define objects called CSPs, in particular two CSPs. CSP stands for constraint satisfaction problem. And here we are given as input a graph on vertex set V and edge set E. We are also given an alphabet set sigma and constraints, which are for every edge, you say the pair of alphabets that are satisfied for the constraint. And so we have a set of pairs of alphabet that are satisfied for every constraint. And the goal is to sort of find an assignment which assigns one element in the alphabet set to every vertex so that you satisfy as many constraints as possible. What does that mean? Let's just say it. You want to find an assignment which is giving an alphabet, giving a letter in the alphabet set to every vertex, such that if you take an edge, then the probability that the assignment given to the two endpoints of the edge is satisfying the constraint is maximized. Okay. For instance, you can think of in the NP world, this can be 3 coloring, and your alphabet set sigma is 3, and your pi e for every edge are all those pairs that are not the same. Okay. What do we know about this problem, 2CSP? It is canonical to the celebrated PCP theorem of NP, and we know that it is NP hard to approximate it to 0.99 factor even when the alphabet set is just of size 3. And now we can ask, And one of the highlights of this PCP theorem is that it is the bedrock of all hardness of approximation results in NP. So once we had this, every other result followed by either a simple gadget preserving reduction from this, or tailoring a more specific PCP that was needed for the problem that we want to end up with, and developing a very more careful gadget reduction, gap preserving gadget reduction to the problem we wanted. But there were no other techniques. It was just one thing, like we had one standard framework for all problems in NP. And ideally, what we want to do is the same for FPT. Like on parameterized complexity, we want to do the same thing. We want to prove one big result, and then everything else more or less follows from this big result. So what is that? What would that be for in the W1 hardness world? So we want to look at the same 2 CSP problem, but when we parameterize by the vertex set. So you have a graph on k vertices, let's say, and O of k square edges, and every edge is a constraint, and your alphabet size is your input, which is n, and your constraints are also given, which is part of your input. And you want to determine an assignment to every vertex so that you satisfy as many constraints as possible. Naively, you can just go over all n to the k choices, and you can solve this in n to the k time. And the question is, can you do better? And it is W1 complete. So we know that there are no FPT algorithms for this problem. So now we can ask, are there approximation algorithms running in FPT time? So is it W1 hard to approximate? And as suggested, I think that this is morally the equivalent of a PCP theorem for parameterized complexity. And with some modifications, if we were able to prove this, we should have been able to prove all the 3 previous results that I spoke about. And in some sense, because we are not able to prove this yet, we had come up with some ways to circumvent proving this and prove the other results that we have. And this was formalized very cleanly as the parameterized inapproximability hypothesis, that there exists some constant delta greater than 0, such that 2 CSPs on k vertices and alphabet size n is W1 hard to approximate to 1 minus delta factor. Or in other words, given a 2 CSP instance as input, it is W1 hard to distinguish the case when there is a satisfying assignment that satisfies all the constraints, versus the case where every assignment fails at least a delta fraction of the constraints. Okay, so this is the hypothesis. And this is still a big open problem, so I want to highlight this. And I will be coming back to, the reason I'm defining it so early is I will be coming back to the case where it's easier to define all the proof techniques if I just go through this problem. So wishful thinking, if we had this, how the proof would look, and we don't have it, so what do we have to do to circumvent it? Okay, so now I'm going to speak a bit more about the techniques involved in proving these results. I'm going to focus on the k-clique problem. And first, I'm going to talk about how to get a constant factor hardness for the k-clique problem. And then how do we get the more stronger, almost polynomial factor hardness for the same k-clique problem? Okay, so any questions so far, or was it fine? Guessing it's fine. So in order to highlight some of the next things, I want to talk of a reduction which is popularly in literature called FGLSS reduction. FGLSS reduction, FGLSS corresponds to the names of the authors who came up with this thing, was the first hardness of approximation results for NP, which made this connection between PCPs and hardness of approximation. And this eventually gave the tight n to the 1 minus epsilon hardness of approximation we know for the clique problem in the NP world, using additional ideas such as randomized graph products and so on. But before that, I want to show that we can just take the same reduction and assume the parameterized inapproximability hypothesis and show that k-clique is W1 hard to approximate to any constant factor. Now, of course, this would mean nothing because we don't know if we don't have a proof of TIH yet. But this is a good starting point to see how such a reduction should look like. So I want to see the proof of this result. So our starting point is going to be a 2CSP. Our end point is going to be a k-clique instance. Okay. So we start from a 2CSP. So we have a graph, we have an alphabet set, and we have constraints on every edge. What we will build is a new instance, a new graph, H, which is going to be the instance of the k-clique, where K is the number of edges in the 2CSP. In other words, a vertex in the new graph H is going to correspond to a pair, first indexed by an edge in the original graph, and then a pair, a satisfying value for the constraint, a pair of alphabets, assignments that satisfy that constraint. Okay. Now, when do we, so we have defined the vertex set of H. When do we put an edge? Well, edges in H are simply corresponding to consistent assignments. So you take two vertices in H, these correspond to two edges in G. If these two edges in G never were incident on a common vertex, you just put an edge anyway. But if these two edges in G were incident on a common vertex, then their assignment to the vertex should be consistent. And since a vertex in H is both having a pair of vertices and an assignment to them, if there is a vertex that is in common to them, it also has an assignment to each of them, and they should be consistent. So this is the only time you check. Otherwise, you just put an edge. So in other words, you can locally, what an edge is doing in H is locally checking consistency of edges. Okay. Now, in the completeness case, if we had a satisfying assignment, then there is a clique of size, the number of edges in the original graph. Why is this? I can look at the specific thing I have written here, which is all those vertices in H, which correspond to the edges of the, so for every constraint, you have a pair that satisfies it. So for every edge in G, you have an assignment to the endpoints of the edge which satisfies it, and that corresponds to a vertex in H. So you just pick all those vertices, and because you're picking it from a global satisfying assignment, everything is going to be consistent. So this will form a clique.
Karthik, there is a question from the audience.
Sure. Let me just check. Oh, okay. I can repeat that. Sure. Right. So the definition of the k-clique graph H is going to be a pair. The first part is going to be, so you're going to go over all edges in your graph G. And for every edge, you're going to look at all the pairs of the alphabet that are going to satisfy that particular constraint. And for every such pair, you're going to have a new vertex in H.
Okay, so thanks. So this is really not only the constraint, but we go over all possible such constraint pairs. Like I mean,
Right.
each, right? That's okay. Thanks.
Right. Like just to elaborate, like if sigma was just 1, 2, 3, like that was the alphabet set, and your pi e was just taking all pair sigma times sigma such that they are not the same, like in 3 coloring, then an edge would be E, which is an edge in G, and then say comma 3, 1. That would be a vertex in H.
So, but would we have like each E and 3, 1, 3, 2, and so on?
Yes, you would have E, 3, 1, E, 3, 2, E, 1, 3, and so on.
Okay, thanks. There we go. That's the point I missed. Thanks a lot.
Great.
So actually, just to be clear, the notation for the graph where you write e comma pi e, is that really what you mean, or just because I thought pi e was the set of like in
it should be just an element in pi. Thanks for pointing it out.
Okay, yes, good. That was also why I was very confused.
Thanks for pointing it out. Thank you. That was a good clarification. And in the completeness case, if we have a global satisfying assignment, you can find the particular local satisfying assignments. By restricting it to every constraint, you're going to get a pair of assignments to the endpoints, and that's going to correspond to a vertex in H, and they're all consistent with one another. So you have a clique. And in the soundness case, again, the notation is E comma element in pi E, as you have pointed out. And from this, the idea is that you can recover an almost good global assignment. Because for every E, so in your set T, for every E, you cannot have two different pairs of elements in pi E, because that would contradict their assignment value and wouldn't be an edge. So T would not form a clique. So for every vertex in G, you either have that they have a consistent assignment through T, or there is no assignment at all. But if T is of large enough size, then we know that we'll recover an assignment to most of the vertices in G, and hence satisfy most of the constraints, and hence be able to go back and build a global constraint. So this is more or less the high-level idea of how FGLSS reduction works. Is there any question before I move?
Yeah, so what do you mean by like most of the constraints? So this is not, I mean, the way you wrote it down, it's not an exact reduction because not every variable will get like an assignment?
Right, because T might just be of size, say T is a clique of size K, which is the number of edges in the original graph, times 1 minus epsilon.
Times 1 minus epsilon. Okay,
right.
But if it was exactly...
if it was exactly, then you will go back and recover.
Okay, that was...
So,
yes.
Right. And from this, you're going to get that k-clique is hard to approximate to 1 minus epsilon factor. And using the standard graph product, you can amplify it to any constant. Okay. So that is what we have. So this is the FGLSS reduction. And of course, the big point is we don't know if PIH is true. So this doesn't really prove anything. But this helps me highlight a very important observation of Lin. And this is really surprising what I'm going to say next, because somehow this observation was lost in the last 30 years in the entire hardness of approximation community. And Lin managed to find this very crucial observation, which is that if your CSP was not, if it was not on some arbitrary graph G, but was on the Boolean hypercube, then you can say something stronger. So in order to say this, I want to define what the Boolean hypercube graph is. The Boolean hypercube graph is where the vertex set is 0, 1 to the t. So there are 2 to the t many vertices. And the edges are that you have an edge between two vertices u and v, if and only if they differ on one coordinate. So you get u from v by flipping one of the bits. Okay, so this is the Boolean hypercube graph. And now we can say the following weaker version of parameterized inapproximability hypothesis, which is that there exists some constant delta greater than 0, such that if you're given a 2CSP on not an arbitrary graph, but a Boolean hypercube graph over an alphabet of size n, it is W1 hard to distinguish the case when it has a satisfying assignment that satisfies all the constraints versus the case when for every assignment, there exists an I, such that if you just look at the constraints on which you only change the ith bit, in that a constant fraction of them are violated. So let me try to repeat this again. So you can look at the constraints of the 2CSP when it's defined over the Boolean hypercube graph. These constraints can be partitioned based on the direction in which they are in. So if you're changing on the ith bit, you're part of the ith set of constraints. And you don't want that in the soundness case, unlike in the parameterized inapproximability hypothesis, you wanted a constant fraction of the constraints to fail. But here, you're not asking for a constant fraction of constraints to fail. You're asking for, in one of the directions, a constant fraction of the constraints fail. So overall, you're only failing 1/t fraction, which is not a constant. It's
just to be clear, I mean, like in the same as in the PIH, like K is taking the role of QT, so somehow QT is sort of fixed. So is there any reason to feel like
QT is fixed, but the constraints are still up for the input graphs, right? Like,
right, but sort of 1/t is sort of a fixed. I mean, it's getting smaller. Yeah.
It's a parameter, right?
Yeah.
Like in the original case, right? Like even if it had a graph G, you had at most 1/k square edges. Like you have k square edges. So even if you're failing just one constraint, it's 1/k square.
Right.
And here it's, instead of that, it's 1/t, which is still some function of k, like in the parameter in some sense, like because
so it's like 1/log k fraction.
Right.
So that's still quite a lot, but you don't need to go to constant. That's the main point.
Right. And let me just say that we still don't know a proof of this either. But this is an important observation that we can work with this weaker version. And we can say the following, that even with this weaker version, approximating k-clique to some constant factor is W1 hard. If you do the exact same reduction that we just did now, and you just do the analysis of it, it will take a while to analyze it, but believe me that you can analyze it and say the same, come to the same conclusion. And this is quite important because this was sort of missed or glossed over in the NP world for 30 years now, that you don't need the full power of the PCP theorem. You had a weaker condition and it still suffices to rule out constant factor approximation. So this is the first observation. So now that I've described this observation, I want to outline what actually Binkailin does. So his result is, the starting point is the k vector sum problem, which is known to be W1 hard. I'm going to define it in the next slide. And then prove an even weaker version of the problem we just saw, which is weak parameterized inapproximability hypothesis, an even weaker version than what we just saw. And after proving that, because we are proving an even weaker version, the reduction to k-clique cannot be as we just saw before with using the FGLSS reduction. So he comes up with a very careful modification to the FGLSS reduction to make everything go through. And I'm going to sort of highlight how each of these moving parts work. Okay. So what is the k-vector sum problem? Here you're given k collections of vectors in h times log n dimensions, where h is some function of k. And there are n vectors in each collection. And the goal is to determine if there are k vectors, one from each collection, such that they sum to the all zeros vector. Okay, so this is the k vector sum problem. It's a generalization of the k sum problem where you want to find k integers that sum to 0. And this is known to be W1 hard even when H is like k square, order k square. There's a direct and simple reduction from k-clique where you try to encode edges and vertices as sort of computation over F2. Okay, so this is the k-vector sum problem. And then we need some technical tools. The first one is some function, because here it's just summing to 0. We don't really like that. So we wanted to sort of hash in a better way. So you need some encoding function which sort of stretches the bits to 2h log n. And what does it do is much more nuanced to tell. So I'm going to wait for a bit. But think of G as some error correcting encoding function. And then we have this very special subspace, which is just determined by the first h coordinates. And what we will do is eventually hash it to the subspace. And there is an operator we need. But here is the more important point. We want the function g to have this property that if I take any k vectors in U is just the union of the U1 to UK, and I look at their, I sum them up and I look at them under G, it should be non-zero. So you have n to the k possible vectors, and all of them should map to a non-zero vector in G, under G. That's the first thing. And the second thing is a more nuanced reasoning that if you look at these vectors, you map them under G, like you take any, say, U, V, and W in your original space, and you map them under G. And after that, you try to hash them down. Then you sort of get different hashes based on, even if you use alpha and beta to be different, you get hashed to different things. So there are some hashing properties that we need. I can come back to this later if needed, but I think it's, to go into details would be a bit of a distraction. But let me tell how the CSP is constructed, assuming this taken for granted as a black box without trying to understand them very well. The CSP is constructed as following. So we are starting from the k vector sum problem. You're given k collection of vectors, and you want to find one vector in each collection that sum to 0. And we're going to building a 3 CSP, not a 2 CSP. So 3 CSP means that every constraint is going to have 3 variables instead of 2. So you wouldn't be able to write it as a graph in some sense. You would need a hypergraph. Our variables are going to be f2 times h to the k. And these corresponds to, in some sense, the seeds of the hash. And the alphabet is the final thing we end up in, which is 2 log n. But here's the more critical point, that for any alpha 1 to alpha k, so these are k seeds to the hash, you're going to map it under to the vector which sums to, you take each seed, encode your vector ui, and then you hash according to that, and then sum them up. Now, of course, if u1 to uk sum to 0, then g of ui's, the summation is a linear thing. So if g of 0 is 0, so this whole thing becomes 0. And what are the constraints? So you have 3 kinds of constraints. Because we're encoding using linear functions, the first constraint is just checking linearity. So you have linearity testing, that the hashed value at alpha 1 to alpha k plus the hashed value at beta 1 to beta k is equal to the hashed value of alpha 1 plus beta 1 plus 2 up to alpha k plus beta k. And then there is a membership testing, which is you look at the hashed value at alpha 1 to alpha k, where on the ith coordinate you have added an extra alpha, and then you subtract it from the hashed value at alpha 1 to alpha k. And from this, you should be able to recover the hashed value at alpha. And then you want to know that this hashed value actually corresponds to some vector being encoded. So if there is some u in ui such that it's actually equal to this, then you're good. And then finally, there's the zero testing, because you want to know that things should sum to zero. So you have that if you shift everything by a line, which is alpha, then things are mapping to the same thing.
Karthik?
Yeah.
I have to, I'm a bit lost in the notation. So like, where did the alphas live in the U's? I think yeah.
So each alpha 1, alpha 2 up to alpha k live in f to the h. So h dimensional space over f2.
But the variables of your CSP are every point in f2 h times k?
Right.
So alpha 1 through alpha k, is that an assignment? No. Like
no, that's a variable, and an assignment to
it's
that.
A variable. Okay. Okay.
Right.
Okay.
And in some, yes.
And you're saying for each, so what is this implication? What does the first line mean? Assignment.
An assignment to the variable alpha 1 to alpha k is taking what it's supposed to mean is that in your mind, you have this solution u1, u2, uk with sum to 0, right? And and you want the alleged assignment in the yes case to be that you take these vectors u1, you take the ith vector ui, you encode it using G, and then you hash it using alpha I. The alpha I is provided to you by the index of the variable.
I see. So this is the desired assignment.
Right.
Okay. But the real assignment is sigma, and you want to somehow make it so that the real assignment kind of equals what you would hope it equals.
Right. If it doesn't, then you violate a lot of constraints.
I see.
And somehow these three constraints, the linearity enforces that you can't just have sigma to be anything. It has to be a linear function.
I got it.
And the membership then makes sure that, you can't be just some linear function, but you need to sort of agree with some vector on every ith coordinate. And then the zero thing enforces that, you can't just be some k vectors in my collection, but they have to sum to 0.
So the only place G appears is the magic G appears is in the second.
Right, because you need to check if it's the encoding of one of your vectors.
Yeah.
And notice that in the previous slide, I had that the G sort of maps to individually. So there's no collisions under G. So you don't get any wrong answers or false positives.
Okay.
Okay, so what he does show is that for this CSP, in the yes case, you satisfy all the constraints. In the no case, either you fail a constant fraction of the linearity testing or a constant fraction of the zero testing, or for some I in K, one of the 1 to K, you fail a constant fraction. So this is the weak version of the weak PIH that I was referring to. But of course, it's so nuanced that it takes a while to say these things precisely. And then the construction of the graph is fairly interesting, because notice that the linearity testing is a CSP on arity 3, because it has the variable alpha 1 to alpha k, it has the variable beta 1 to beta k, and it has the variable alpha 1 plus beta 1 to alpha k plus beta k. So there are 3 variables involved in any constraint. Whereas the membership and the zero testing involve only 2 variables. So what he does is something very clever, that he forgoes testing linearity while building the graph and just says, I'm going to build the graph over all pairs of variables and assignments to them such that by definition, they should sum. That alpha and I, so each vertex in my graph is going to be an alpha and beta, and I'm going to automatically check and only allow those assignments to alpha and beta such that alpha, the assignment at alpha plus assignment at beta is equal to the assignment value at alpha plus beta. And once he does that, then he has encoded the linearity testing as building the graph, then the edges, which are all 2 arity constraints, can just be checked using the standard edges that we had in the FGLSS as membership and zero testing. And from this, he's able to show that approximating clique to 1 minus epsilon factor is W1 hard. And then using graph product, you get constant inapproximability. I'm guessing that this was not as clear as I had hoped.
But so this 3 CSP construction, so you're saying that if all the tests succeed, then you can extract these U's.
Right.
Okay. But if they don't succeed, then the special failure case that you said is that for at least one I in the membership test, I mean,
for at least one I in the membership test, your constant fraction of the constraints fail.
Right. Okay. So what does that do? So this is the weak PIH, but maybe with 3 CSP as opposed to 2 CSP? Is that?
Yes, but it's not exactly over the Boolean hypercube because the zero testing edges don't correspond to edges in the Boolean hypercube. So if it's only the membership testing, then it is exactly the Boolean hypercube. But you have these 3 arity constraints from linearity testing, and you have these weird edges from zero testing, which are like through the origin in some sense. So you have these nuances, but they don't really affect the argument so much.
I see. And then there is yet something else that happens to transform this into clique, or like
so there is a way to handle there's a very clever way he handles linearity testing, which is he doesn't even bother to encode them as edges in the clique graph. He just forces them to be the right vertices are the ones that satisfy it. And once he does that, then the remaining are all, you're back to a 2 CSP. So you can go back to your FGLSS reduction. So then he falls back, yes.
And then the reduction you already showed us on, I guess, this graph at the bottom.
More or less works, yes. At a high level, that is the intuition.
I see.
Okay, so I'm going to just spend a couple of minutes on what modification we had to do. So I don't even attempt to tell the proof ideas of ours because that would read a lot more time. But let me just mention a few ingredients that we had to do on top of this. So first thing is that by starting from F2, the linearity testing, you cannot hope to get a gap better than half. That's just because of the field size. So we had to start from FQ, whereas from Q is some very large prime. But then we had to end up doing, we don't have linearity testing so clean. So we had to use list decoding. So you wouldn't, unlike in his case where you would get one linear function which agrees with things, here you would get a collection of linear functions. And what that does is adds a lot of noise in the arguments. So none of the arguments I previously said go through as nice as they did. And everything has a lot of noise and you have to handle everything with a lot of care. And if we do all of this, then things go through. So the main idea being that you extend working from F2 to FQ. And so now you're looking at the Q array cubes. And in that, things no longer are edges, but are more like lines. So there's a different kind of geometry to handle. And we, on top of that, we have list decoding, which is a collection of solutions instead of one. And you have to sort of carefully go over each one and say things are not going too out of control. So that's the most I would want to say at this point. So again, to remind, the state of the art is that we can rule out k to the little of 1 factors. And really the answer should be that for, instead of saying approximating k-clique to any k to the little of 1 factor is W1 hard, the real answer should be approximating k-clique to any k to the 1 minus little of 1 factor is W1 hard. And this we know how to show from gap ETH. So it's just that we don't have a technique to do it from W1 hardness. And so this is like the real bottleneck. And it seems like the current framework which Binkailin has established has, this is the bottleneck. And it's hard to go past where we are without new ideas, really new ideas. Okay, so now let me make a few high-level remarks. How much time do I have? 10 minutes more?
You have about 10 minutes, yeah.
Okay, good. So again, just to recap, the big prize here is to prove the parameterized inapproximability hypothesis for 2 CSPs. And actually, looking at this recent work of Binkailin, everything falls in better perspective, because now we understand why a lot of things happen the way they happen. For instance, we have hardness of approximation results for K set cover, K set intersection, and k-clique. And we also have it for, say, some K Steiner orientation. But let me simplify the discussion to these 3 problems. And each one of these results has its own gap creation technique. Like they use different things, they work different ways. Each one is different from the other. And to specify the K set cover result that we have, uses just basic error correcting codes. It doesn't use anything more than distance of error correcting codes. And the K set intersection, which Binkailin has shown, uses extremal graphs, which are called norm graphs. And under more sophistication, just random graphs would suffice. And recently, I have a paper in this Fox, which uses random algebraic constructions as well. So these are very different set of techniques altogether. And now we have this k-clique result in which Binkailin uses locally decodable codes, and we use list decodable codes. Like the tools have gotten weirder and very heavier and more analytic. And it's unclear, like, why do we have different kinds of techniques for proving each result? Whereas in the NP world, it was like we had PCP theorem and then everything follows. So this was a bit weird. And it turns out that now in perspective, these are all just coping mechanisms because we cannot prove PIH. So because we cannot prove PIH, we have like all these weird techniques to prove the result we want without going through PIH. And this is both a boon and a bane, because in the one hand, this is like we have to sort of circumvent proving PIH. So like we have made our life much harder. But on the other hand, this is in stark contrast with the NP world. So we are able, so parameterized complexity is able to say something which the NP world couldn't. That look, NP, it's able to do this more fine-grained analysis of NP hard problems. Like, oh, K set cover is so hard, you don't really need the PCP theorem. There is some easier ways to prove these things in the FPT world. And K set intersection can use different things. So it sort of shows the nuances between the NP hard problems, which is hard to see in the NP world. And also gives the hope that maybe if we can prove PIH, then we get this unified framework. And then the rest of the results that we have to prove in parameterized complexity would just be prove some stronger version of PIH and use some better gadget reductions. And that's it, which would be great, because things should, if things follow in a unified framework, that leads to better understanding of why things are hard. Okay, and talking about PIH so much throughout this talk, there was a recent paper where they showed that if we can show constant approximation algorithms for k-clique problem require at least n to the k over log k time, then PIH is true. The idea is you can reduce k-clique to k bi-clique with some gap, then amplify the gap by sacrificing the running time, and then use these density Turan type solutions of density versus bi-clique absence, density of edges, to say that there is not a large dense subgraph. So this is one very nice approach, that this would necessarily imply that if you assume ETH and you have a strong result for k-clique without losing too much in the parameter, then you can show PIH. Of course, we are very far from this result, because both the previous result of Binkai-Lin and our result proves a very weak time lower bound on constant approximation of k-clique, which is n to the log k to the omega 1 instead of n to the k over log k. And in this paper, which was recently released, they were able to improve the exponent in the log k, so the exponent of the exponent, to 1. So this said, I want to also just say that this is a very good time for the community to sort of look at all these W1 hard problems and try to see if we can prove hardness of approximation, like these very specialized problems, instead of more foundational problems like clique or bi-clique, very specialized problems, and try to see if they are still W1 hard, assuming PIH, because the sense is that PIH should be provable in a few years. And we would want everything to just fall in place right after we prove it. So one is to sort of replace all the results we know from gap ETH with PIH, and whatever we know from PIH, maybe replace it with clique, because we already can prove hardness of approximation for clique. And in general, just try to look at all the problems you have showed W1 hardness in the past and try to see if we can prove hardness of approximation to that. I guess this is more or less my time. So.
Okay, so thanks a lot, Karthik.